In section 14.4, we're going to be talking about continuity. Our objectives are to determine if a function is continuous at a point, determine if a function is continuous on an interval, and apply the properties of continuous functions. So informally, continuity can be explained as if you let c be a real number in the domain of the function, then it's going to be continuous at a point C if you can draw the graph of f at that particular point without lifting your pencil from the paper. So I have 4 examples here where that is the case. So in each case you see C, okay, C for each one. Now if I attempt to draw the graph of each one of those, like around C, then you notice that I can do that without picking up my pencil. So what that means is that these functions are continuous at x equals c, and a function is continuous at x equals c if the graph around that point cf of c, okay, which is here, 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 and here, can be is connected and it's unbroken. So when we're talking about calculators, or when you're using calculators and you graph, your calculator can be a little misleading because with asymptotes, it's not going to graph the asymptotes. It's just going to look sort of like a line on your calculator, maybe something like this. So caution, this is just use caution when you're using your calculators in determining discontinuity. So the definition of continuity is going to be if you have a function that's defined for all x on an open interval containing c, then f is going to be continuous at x equals c if, first of all, f of c is defined. Okay, so we have to be defined. If the limit of f of x as x approaches c, first of all, it does exist, and then if that limit is equal to f of c. And we're going to see an example of that here in a few minutes. I think I skipped a page, so let me see. Okay, I did skip a page, so let me go back for a minute. Okay, so I talked about this in a continuous function, so I need to talk about disk functions that are not continuous at a certain point. So when we talked about the ones that are continuous at points, all of these, you can draw them as without picking up your pencil. So the ones that are not continuous are examples like these. So there's a break in the graph. So if we're talking about at the point x equals c, and I try to draw this, there's a hole here. Okay, so I have a jump in the graph, and the same thing here. Okay, I have a hole, I have a jump. Here I have an asymptote at x equals c. It's not defined, and then here I have a hole. So I got a little bit ahead of myself here. So a function that's discontinuous or not continuous is at x equals c if there's a break, a gap, a hole, or a jump when x equals c. Now, we've talked about the calculators. So to talk about continuity, then you know that f of c has to be defined, and we saw that in the last example. The limit has to exist, and that limit has to be equal to f of c. So our first example is going to be to show that the function f of x is continuous at x equals 3 without graphing. All right, so if we're going to do this without graphing, then the first thing we're going to do is we're going to make sure that f of c is defined. That was the first thing that we needed to look at. So if we're looking at f of x and we want to state its domain, the domain is going to be all real numbers except for whatever is going to make that denominator 0, and then we can't have those values. So it's going to exclude those values. So take the square root of both sides, and you know that x cannot be 0. So it's all real numbers except for x equal to 0, which means that that f of c is defined. Okay, because we're talking about at x equals 3, not at x equals 0. All right, and then the next thing we're going to look at is whether or not the limit of f of x as x approaches 3 in this case exists. So the limit as okay, so here's our limit. We're going to have to do a little work on this one. This can be rewritten as from our properties. Okay, so we rewrite it as that. And once we do that, then we can start to evaluate. We know that we're going to get root 6, and then we get negative 1 times negative 1. And that's going to be over 9, okay, which is going to give me negative root 6 over 9. Okay, so the limit does exist, and it's negative root 6 over 9. Now, the third thing we have to do is we have to make sure that when we evaluate and we find f of 3, that we do get the same thing as this limit here. So that takes care of number 2. So the third thing is that we're going to find f of 3. Okay, so when we find f of 3, we get 2 times 3. All right, and that simplified is going to give us negative root 6 over 9. Okay, now what we are able to say is that f of 3 is equal to the limit of f of x as x approaches 3. So all three of those combined tells us that, without graphing, that this function f of x is continuous at the point x equals 3. So let's talk about the continuity of special functions now. The first one is our polynomial function. These are those nice functions with no holes, gaps, jumps, no points of discontinuity. So they're going to be continuous at every real number. Our rational functions are going to be continuous at every real number also, except for those that would be excluded from the domain, or those that would be undefined, produce a 0 in the denominator. For our exponential functions, those are going to be continuous at every real number. For our logarithmic functions, those are going to be continuous at every positive real number. And then for our trig functions, sine of x and cosine of x are continuous at every real number, while tangent of x is only going to be continuous at the real numbers that are in its domain. And so if we think back about the graph of tangent of x, h of x equal to tangent of x, we know that we have some asymptotes, okay? And those asymptotes occur at negative pi over 2 and pi over 2. And they occur in intervals of pi. And so my graph is going to look like this. Okay, so it's defined, and this should actually go through the origin. So it's defined here on the green, but when we get to the pi over 2, negative pi over 2, at those values, it is not going to be continuous at those values. So let's talk about the continuity from the left and the right. A function is going to be continuous at the right at x equals a if the limit of f of x as x approaches a from the right-hand side is equal to f of a, and a function is continuous from the left-hand side at x equals b if the limit of f of x as x approaches b from the left-hand side is f of b. So what that means is, let's actually draw some graphs here to help us out. Let's make this... So this might be a little hard to understand, so I'm going to try to make this a little easier for us to understand. Let's start with two graphs that are almost exactly the same. And so the first function, I'm going to have a b on here, and this one is going to look something like this. And then open circle, and all right, and on the second one, it's going to look pretty much exactly the same, except for we're going to have an open circle there and now a closed circle here. Okay, so let's talk about when those are continuous. Okay. And of course, we're talking about continuous and discontinuous at points B, and we're going to call this one point A. Okay, points B and A here that we're talking about continuity at those points. So on the first one, it is going to be continuous from the left-hand side, because as you move, you notice as you move here from the left-hand side, we do approach this value f of, this would be f of b right here. Y value that we produce is f of b. So it's defined at that point. That was one of the things, is that it has to be defined. So this is going to be continuous. From the left-hand side. And then when we're talking about the green here, this one is going to be continuous from the right-hand side, because it is defined here. And this would be f of a. Here, that would be the y value, because it's defined at that point. It's not defined here at this point. Okay, so, and we'll call this one g of x. This one's f of x. Okay, so it's defined from the right-hand side. And so for discontinuity, this one is going to be is not continuous at f of x when we're approaching b from the right-hand side, because it's not defined. It's not defined at that point. And then for our green one, g of x, it is not defined as x is approaching a from the right-hand side, because we are not defined here. Okay. Okay, now we have an example, and we want to show that f of x is continuous from the left at x equals 3. So the first thing I'm going to consider is the domain of f of x. So we know that the domain of f of x, we know that the radicand has to be greater than or equal to 0, which means that x is going to be less than or equal to 3. Now, if we think about that on a number line, that looks like it's 3 here, and we're moving this direction. So can we approach 3 from the left-hand side? Yes, we can approach it from the left-hand side. Can we approach it from the right-hand side? No, we cannot, because it's not defined there. So that tells me, first of all, yes, it's possible. Now, the next couple of things I have to consider is I have to find f of 3, and then I want to know that that f of 3 is going to be the same as the limit of f of x as x is approaching 3. All right, so f of 3 is just going to be 0. Okay, now my limit here is going to be since we know that can be rewritten as the square root of the limit of the 3 minus x. So then that would give us the square root of 0, and again we get 0. So then we can conclude that the limit of f of x as x approaches 3 is equal to f of 3, which means that this function f of x is continuous from the left at x equals 3. So now for continuity on an interval, a function is going to be continuous on an open interval AB if the function is continuous at every value in the interval. And a function is said to be continuous on a closed interval AB provided that it's continuous from the right at x equals A and continuous from the left at x equals B. So, and that's for every value. So the difference, so the first one I talked about, and then the second one. So on an interval from A to B, so here we have A to B, A to B. We have an open interval looking something like this, maybe. All right, while the closed interval is going to look like this. It includes, it is defined at x equals a and defined at x equals b. So now we're going to look at an example, and we're going to talk about the continuity of the graph that we have here. So first of all, let's just come up with the points where it is discontinuous. Let's see. Uh, okay. My graph has gotten a little off here, so let me try to move that back to where it should be. Let's work with that, okay? Okay, so well, I just can't get my graph right. Okay, let's just leave it like this. And let's talk about our points of discontinuity. We've got some breaks in our graph at 2 points. We've got a break right here. Okay, and then we have another break here. So we have a break in the graph at -1, and we have another break in the graph where x is 3. So, all right, and then we have different intervals here. Okay, so the first interval is going to be from where x equals, that's -1, 2, 3, 4, 5, 6, -6, all the way up to where it's -1. So that's our first interval. We have something going on. It includes 6, so we're going to use, -6, so we're going to use a bracket. It includes -1 on that first interval, so we're going to use a bracket there and a comma. Then the second interval we're talking about is going to be starting here and ending here. So that's going to go from -1 all the way to +3. And those are open circles, so that means it does not include those values, does not include -1, does not include 3. So we have parentheses instead of a bracket. And then the last one, so we're starting here and going to infinity. So we're going from 3, that includes 3, so we use a bracket, all the way to +infinity, use a parenthesis. So it's continuous on the intervals from -6 to -1, and then from -1, 3, and from 3 to +infinity. Okay. The properties of continuous functions are if you have two functions f and g and both f and g are continuous at point C, then the sum of those functions f plus g is going to be continuous. The difference of those functions f minus g is going to be continuous. The product is continuous and the quotient is continuous. All right, so we're going to look at an example of using this. Here we have two functions, f of x and g of x. One is a trig function and the other is a polynomial function. So both of those are continuous at x equals 1, and we want to prove that the others are continuous. So I need to add parentheses here to a. I forgot to put those in. So this here can be rewritten as f minus g of x, or it can be rewritten as f of x minus g of x. Either way is fine. But knowing that, and I know that f and g are both already continuous at x equals 1, so I know that the difference of those two functions is continuous at x equals 1. So for b, this one can be written as f times g of x, and therefore it is continuous at x equals 1. This can be rewritten as f, the quotient, and so it is continuous. And the last one can be rewritten as f plus g of x. And so it is continuous. Now for continuity of composite functions, if you have a function f and it's continuous at x equals c, then the function g is continuous, and then you have another function g and it's going to be continuous at x equals f of c, then the composite function g of f is also continuous at x equals c. Now that's sort of a lot that you have going on there. So the key is that you have composite functions here, okay? So you've got this x of c, you're plugging c into you're finding f of c, and once you have that, then you are taking that f of c and plugging it into your next function g, and to find out if g of f is continuous. Now, this still might not make much sense, but I think after we do the next example, it'll make a little more sense. So I'm just going to leave it at that for right now. And then we have the intermediate value theorem. If the function is continuous on a closed interval from a to b, and k is some number between f of a and f of b, then there exists at least one number between a and b such that f of c equals k. So let's look at a graph to understand that one. And this one is sort of one of those that we probably are going to understand pretty easily after I do this. Let's say I have a closed interval here, and this is where x is a, and this is where x is b. And it's continuous along that interval, as we have here. This is a closed circle. Then what I have here, this right here, this y value is going to be f of b, because that's b there. And so when we plug in that b, we get f of b. And this right here is f of a. Okay? So if we just choose some value, so it might make more sense even to think that your f of a is down at -4, your f of b is up at +4. If I choose some random value they call k here between f of a and f of b, so maybe I choose 2, then that 2 is going to have a place, or it is going to be defined for this function. So if I look where it's 2, then yeah, here we go. There's going to be an x value that's going to produce that 2. And that's what the intermediate value theorem is trying to tell us. Okay, so now let's see if we can clarify that continuity of composite functions. Here we have an example. I have h of x. We have a somewhat complex function, and I want to take that and see if I can use composite functions to simplify it a little bit. So what I can do is I can say, all right, I want to come up with this g of f of x. I'm going to rewrite this as g of f of x, where my g of x is just going to, or where my f of x, let's say my f of x. My f of x is just going to be what's inside here, okay? And that is a polynomial function. And then my g of x is going to be that square root of some value. So now if I look and actually work through the g of f of x, then that's going to be g of f of x is equal to g of, I replace the f of x with the actual polynomial, which is x cubed plus 2x squared minus 3x minus 4. And then I take that value and replace the x in my g of x, and that's when I get that polynomial h of x that I started out with. So that's why h of x can be rewritten as g of f of x, as long as f and g are defined as I have defined them here. Okay. Now, that's going to help us because we want to know if it's continuous at where x is equal to -2. And that property says that first of all we need to find out if our interior one, which is our f of x, what's going on inside here, we want to know if f of x is continuous at this value. And to figure that out, we're just going to find the limit okay, and we want to know that that limit is equal to f of negative 2. Okay, we want to find out if it's equal to f of negative 2. And if it is, then f of x is continuous at x equals negative 2. So to find the limit, we notice that this is a polynomial function, which means all I have to do is plug in negative 2. And when I plug in that negative 2, I get a 2 here. All right? And then we know if we plug in negative 2, then we get a 2. So yes, it is. So f of x is continuous at that point. Now, what this means is that f of negative 2 is 2. And that was part of what we needed to find. So then after you do that, the second thing is to find out if g of x is continuous at x equals whatever this number is. It just so happens that one's, it's the opposite sign of the one we started out with. Okay, but the key is that this here, this value here, is my f of negative 2. It's what I got when I plugged in negative 2 into f. So to do that, to figure that out, we're going to find the limit of, and this I should have used lowercase, of g of x as x approaches 2. And we want to know if that's equal to g of 2. All right, so for the limit of this, then that's going to simplify to limit of x. Okay, so we get that. And g of 2 is just going to be square root of 2. All right, so here x is just the identity function, so we plug that in, we get root 2. It is. So both of them have checked out, which means that, yes, h of x, using composite functions, we've figured out that h of x is continuous at x equals 2. And that's all I have for section 14.4.